looked at using the method called logarithmic differentiation. And let's give you a little heads up. If you differentiate the log of x, the natural log of x, its derivative is 1 over x. If you do a log to some number, like log to base 10 or log to base 3, the derivative is 1 over the natural log of a. So it doesn't matter if that's 10, this will be the natural log of 10. If this is 2, this will be the natural log of 2. You do not turn these into decimals. I know you can go to your calculator and find out what the natural log of 2 is. Leave it exactly that. It'll look ugly, but it has to be there. So if you differentiate log to any base, it's 1 over the log of that base with an x next to it. If you differentiate e to the x, you get this. And if you differentiate a to the x, you get a to the x, and you multiply by that natural log rather than divide. So they're basically guys that you would add to your list of things I know how to differentiate. And we've kind of finished with a logarithmic one, I believe. And
I have a quick question about that.
Yes.
So I was reading something that indicated that the one on top was actually, well, the derivative of the function of the x part.
I'm not sure what you mean, Rachel. So you were
when you take, say, the derivative of the natural log of x and you turn it into 1 over x, that the one on top is the derivative of the inside function of the
it is. You're right. Yes.
Okay.
So I'll show you what you're getting at. If someone went and said to you, I want you to find this guy, it's a chain rule, and the inside function, just like you said, would be sine x. So what we would do here is we would do 1 over sine x with a natural log. Well, I don't need the natural log because it's a natural log already. And then you times the derivative of sine, which is cosine. And so just like you said, isn't the top the derivative of the inside function?
Is that the same case with the regular log base b of x?
So if somebody went and said to you, let's do the log to base 3 of sine x, right, just for example, then the derivative would be 1 over. The only difference is you have a natural log of 3 guy to worry about. So it's not 1 over sine x, but 1 over that fella. So you get that extra log 3, right? That little bit there. And then you differentiate by the top. And when you look at the two answers, they are not that dissimilar, are they? The only difference is you get this little extra piece that you don't get here. Technically speaking, the guy that's here is 1 because the natural log of e is 1, right? So it is the same formula, but just a special case. That makes you happy?
Yeah, that makes a lot more sense. Thank you.
Okay. So as I was saying, we were doing logarithmic differentiation. So I'm going to show you 2 different ways to do question 15, or at least a version of 15. The first one is 9 to the power of t cubed, right? That's the, and I'm going to do it 2 different ways. First way I'm going to do is logarithmic differentiation. So step 1, you take the log of both sides. We're comfortable with that? Step 1, log of both sides. Step 2 is, well, I don't have my laws of logs handy, did I? Did I keep them? I probably threw them away, didn't I? Okay, to remind you the rules of logs, really 3 of them. This one says that you can take 2 things that are multiplied and separate them as 2 logs being added. You can take the log of two things being divided and separate them. Be consistent with their logs. And the third one is that the log of something to the power of n can be written as a multiple of a log. And will you pretend that all of these say logs, because it works for all of them. Now, the natural log of 9 to the power of t cubed can be rewritten as t cubed, the natural log of 9. And I want you to think of that as a number, because it is. Well, step 3 is you differentiate and you get 1 over y dy by dx. If you differentiate t cubed, you get 3t squared. So if you differentiate t cubed times a number, you still get 3t squared with the number, right? It's still there. You then multiply both sides by y. And then to finish, you turn the y back into the original. So you get 3t squared natural log of 9 times 9 to the power of t cubed. And we have now found that guy's derivative. And that is using logarithmic differentiation. I said we do it 2 ways. So here's the same question again, only now I'm going to do it using the chain rule. So this is 9 to the power of something. When you differentiate 9 to the power of something, you get 9 to the power of something times the natural log of 9, followed by the derivative of the inside function. In this case, that guy. And did I change that to I did? It's a cube, right? So you've got natural log of 9, 9 to the t cubed, times the derivative of t cubed. And that guy is the same answer. It's got a 3, a t squared, a natural log of 9 times 9 to the power of t cubed. Now, if you do it with a chain rule, it takes 4 lines. If you do it with logarithmic, it takes 1, 2, 3, 4, 5. It takes 6 lines. You see that this is a much longer process. I would suggest that chain rule is more efficient, but you can choose how you want to do it. So we can differentiate 40 to the power of something, 2 to the power of something. And that something could be anything. It could be x cubed, it could be sine x, it could be whatever you like. And it works quite well. Any questions? Okay, let's chuck you in the deep end then. This one might get some questions. G of x is 2 to the power of c over x. Right? 2 to the power of some weird fraction with an x in it. I'm going to do the chain rule. 2 to the something. Well, when you differentiate 2 to the something, you get 2 to the something times the natural log of 2. And don't forget to finish with the derivative of the inside function. So I'm going to have this guy. C is a constant. So I need to figure out how to find the derivative. So I'm going to do it over here of c over x. Well, if I call it y equals c over x, I could rewrite it like that. And so to differentiate it, I can use the power rule. Multiply by the power, reduce it by 1, and then make it look pretty. So the derivative of that is this. So I go over here and I put in negative c over x squared. And I'll try and make it look pretty. And that's the best I can do. Can you see that this is quite a messy differentiation process? Right? They're not pretty, but they're doable. Right. So differentiate that, you get a log 2 times that, followed by the derivative of this fraction, which we found was this, and then you just move things around to make them look pretty. Any questions?
For the final answer, it says 2 and then c to the x.
C over x, c divided by x.
So just to clarify, as like a general rule, the inside function would be the exponent. And
It'd be the power, yeah.
Yeah. And then is it considered the outside function, the number? Well,
2 to the something is the outside function.
Okay. And then you take the log of that, or the natural log of that number.
Yeah, So okay. Yes, essentially. So if I generalize this, really generalize it, this would be an example of that. If you were being asked to find 2 to the power of f of x, right? Where f of x might be c over x, it might be sine x, it might be whatever. Your answer would be 2 to the power of something with a log 2 at the front, finishing with the derivative of the something. Does that make sense? I'm not, just in a general way, right?
Yeah.
2 to the something gets you log 2, 2 to the something, and times the derivative of the something. So if I call that f of x, you get f dashed. So if I was using this, if somebody said to me, what's that, guy? You would say log 2, 2 to the power of sine x, times the derivative of sine x.
So are we using, this is the chain rule, but we're using logs in it? So it's,
yes, it's a chain rule with logs.
So how is it that you're not taking the natural log of y on the other side?
Oh, because I am not doing logarithmic differentiation here. I'm just doing chain rule. Right, I'm doing this as 2 to the power of something. I'm doing this as a chain rule. If you did logarithmic differentiation on this, can you trust me that 5 lines later you get the same answer? But I'm doing this using a chain rule. I'm thinking 2 to the power of something. The derivative of 2 to the power of something is the natural log of 2 times 2 to the power of something, finishing with the derivative of, in this case, sine x. So I was using the chain rule in that question.
Okay. So 2 to the x is natural log of constant times the
2 to the x. Right? And what's the derivative of x1? So it doesn't matter. Let's try another one of those things. Again, all of these are chain rule, right? Suppose I did 4 to the power of 2x plus 1, right? And I'm going to do the chain rule on it. So that's basically going to be my inside function. So if you differentiate 4 to the power of something, you get 4 to the power of something. What you have here is that extra little log 4, right? And then don't you finish with the derivative of 2x plus 1. And what would be the derivative of this inside function, 2x plus 1?
2.
And so just rearranging it so it looks pretty. There's your answer. Are you comfortable about the chain rule? What I'm doing here is just a chain rule.
Where does the log 4 come from?
It comes from this fella, and the formula for getting anything to the power of x, like 4 to the power of x, is the log of 4 times the original. So if this was 10 to the x, there'd be a natural log of 10 here. This was, a to the x, it would be a natural log of a here. So this is part of the answer. It's always there when you're dealing with powers like 2 to something, 4 to something. Okay. Okay, new change in tack. We are going to add to the list of things that we can now differentiate by adding inverse trig functions. When you were doing 142, you would have seen these three in particular, because these are the three that people typically use. Remember the inverse sine, the inverse cosine, and the inverse tan function, right? I'm actually teaching 142 as one of my classes, and we've just finished this last week. Inverse sine, inverse cosine, inverse tangent. I am now going to tell you what their derivatives are. And I am not going to tell you or prove to you that that is the answer. I'm just going to tell you. But I've done that already. Isn't the derivative of sine x cosine x? And you just have to believe me, right? Remember? Derivative of sine x was cosine. What's the derivative of cosine x then?
Negative sine.
Right, didn't you just do it because I told you, right? Proving it is very difficult to prove at the level, but you know, you do enough math, you'll be able to prove it eventually. So are you just going to trust me that these three answers are just, they are what they are because I'm telling you, right? And you're just going to have to live with that. This fella is not even vaguely what you would have guessed it to be. Wouldn't you probably have thought it might have been the inverse cosine function? Wouldn't that be nice? You know, sine gets you cosine, right? Do you notice that the derivative doesn't even vaguely look like a sine or an inverse sine or anything, right? It's got no connection whatsoever. But nonetheless, that is its derivative. The inverse cosine function has only one minor difference. Do you notice it's negative? And the inverse tan function doesn't even look like the guy. These two, it's quite different. So can you just add them to the list of things I now know how to differentiate? Right. Are we good? Right. Now, I'll leave them there because we're going to be using them a lot. And we're going to start off with nice, easy ones, and then we're going to use the chain rule to do more difficult ones, or various rules, including the chain rule. So, if I said to you, find what the derivative of 3 inverse sine of x, take away this guy, you would say its derivative is 3 of those guys, take away 2 of those guys. But if you take away a negative, you're adding it. So what you've really got is 3 of those guys plus 2 of those guys. You're happy about taking away a negative gets you a plus. And since they share a common denominator, there is your answer. Are we okay with that? If you do multiples of sines and cosines, do one other simple one. Suppose I was asked to find the derivative of 3 inverse tans. The derivative of an inverse tan, just one of them is this guy. So won't 3 of them be 3 of this guy? Now things are going to get really messy really quickly. Suppose I wanted to find the inverse of 2x, right? The inverse function of 2x. It's a chain rule. I want you to think of this x here, not so much as an x, but as a placeholder. In other words, where you put stuff, right? So this x and this x will be the same thing. So if x turns into something else, 2x in this case, So does that. So according to the chain rule then, shouldn't the answer to the inverse sine function be 1 over the square root of 1 take away something? But not take away x. That's what it is if it's inverse sine of x. Since I'm getting the inverse sine of 2x, what do I put here? What gets squared? X gets you x. 2x gets you
2x.
2x. And dead easy to forget this. Times the derivative of the inside function, which is so easy I should do it in my head, but I'm not. This times itself gets you 4x squared. And isn't the derivative of 2x just 2? So there's your final answer. Do you see how it's a little bit sneaky? You don't normally need to do that. In any other question that we've done, we didn't have this funny 2x turning here kind of thing, right? If somebody said to you the derivative of sine 2x, isn't it just cosine 2x times some stuff, right? Nothing much changes, but in this it does. Let's try another one. Suppose you wanted to do 4 inverse tan of x squared. Right. The inverse tan of x is this guy. So differentiating 4 inverse tans gets you 1 over 1 plus something squared. Will I just write 1 plus x squared, or will I put something else? In fact, you know, what's going to go in where my finger is? When it's an x goes here. When it's an x squared, what goes here?
X squared.
Yeah. Times, don't forget, the derivative of the inside function. And that's 2x, and 2 times 4 gets me 8x on the top. And now I get 1 plus x to the 4 on the bottom. Are you beginning to get a little bit happier with this? Right. Try another one. Let's do question 21. The inverse sine of 4x. We're going to find its derivative. An inverse sine gets you 1 over the square root of 1 take away something squared, followed by the derivative, so times 4. What's going to go where my finger is this time?
4x.
Right. You're getting quicker, so that tends to mean you're getting the idea. Isn't it basically this is what I mean by a placeholder, right? See if that's 22y, don't you put 22y there. If that's 40x cubed, don't you put 40x cubed there. You see, that's how it works. And because it's a chain rule, don't you must finish with the derivative of 4x. So that's where that 4 came from, right? It's the derivative of this guy. Now, if you make it look pretty, that's the answer. Okay, let's put you under some major pressure. 22 now. Okay. The inverse tan, its derivative is 1 over 1 plus this guy squared. So it's going to be 1 over 1 plus this guy squared. You happy with that part? Right, 1 over 1 plus something squared, right? Inverse it, 1 over that guy squared. Then you finish with the derivative of the inside function. That's the bit that people forget. The derivative of the inside function. Are you happy with the square root of x squared just gets you x?
Mhm.
Now, something like finding the derivative of the square root of x. Wouldn't you probably call it x to the half? And then you can differentiate it using the power rule. And then you spend some time getting it into a nice format. So when I say the derivative of this guy, we get times 1 over 2 square root of x. And I would rewrite this guy as 2 square root of x, 1 plus x is one big fraction. Are we good? Any questions so far? Let's up the ante and do another inverse tan, but even uglier. And it's going to be the square root of x minus 1 this time. Quite similar, but a little bit different as well. So it's going to be 1 over 1 plus the thing squared, followed by the derivative of the inside function. So I need to find the derivative of this guy. Okay, what should I do to help me get to the derivative? What should I do to the square root of x minus 1? How should I rewrite it? How about that as another way of phrasing it?
To the power of 1/2.
All right. If you think about it, isn't that what you always do in every kind of square root equation? Now, power rule is 1/2, right? The power. Reduce the power by 1, technically times 1, but nobody writes that because it doesn't make any difference. Bring the fractional power downstairs and then turn it into a square root. So we now have 1 over 1 plus. If you take the square root of something and square it, don't you just get the thing? You happy with that x minus 1? Square root of x minus 1 squared gets you x minus 1. The derivative is 1 over 2 the square root of x minus 1. Well, wait a minute, don't they cancel out? So you've got 1 over x times this guy. And you can combine them because it's a multiplication. And we are finished. So inverse trig functions and their derivatives all involve you using one of these three properties that you're told, and a fair amount of algebra as well. So far, so good. Right. Everything I've done so far has been a chain rule question involving those. So let's do a product rule. And it gets me a chance to have a good moan. This is going to be a version of 23. And the function is going to be an inverse cosine of x times the natural log of x. Well, that's how I read it. So let me get my mump over with. The inverse cosine of x has another name. It's called an arc cos. The inverse sine function has another name. It's called an arc sine. And the inverse tan function has another name. It's called an arc tan. Why am I going to have a good mump about this? Nobody I know except America uses arc anything. This is a very archaic way to describe the inverse sine and cosine and tangent. I'm making this up, but I think it might be true. The reason they called it these guys and not this notation is because in the early days of printing, subscripts were kind of hard things to do because they didn't have them. They only had like letters of the alphabet, so they called it arc sin and arc cos, which is fine for like 300 years ago, which is when they probably, maybe a little bit longer than that, when they probably started doing it. Would you agree that inverse sine functions is just much nearer? Plus, from 141, haven't we used that -1 symbol to mean inverse, right? So here's my bump. Why does America still use it? Why are you the only country in the world that would call that an arc cos? Vanessa, I'm putting you in the spot. Why do Americans do that to annoy me?
To annoy you?
Me personally, they just know it's me and they do it. Even when I wasn't alive, they did it knowing that one day I would be alive.
Yeah, we had secret meetings to kind of, get together and say, Donald Robertson, we're going to really get into
You're going to piss him off by doing something that has no, there is no good reason in the world you should ever need to do that. Would you agree? This notation just makes life easier. In math, shouldn't you be consistent? In other words, when a French guy does it, and when an American guy does it, and when a Scottish guy does it, shouldn't we all be calling them the same damn thing? Right? But it's probably the same reason why you use pounds and ounces and pints, isn't it? You kind of get into a rut where, well, we did it 200 years ago that way. Why should we bother changing now? And you might say, well, everybody in the world is changing, but Americans are probably thinking, I think if we keep at it, they're going to change their mind and come back to pounds, right? That metric was just a fad. That's going to go away. If we just stick to pounds, we don't need to worry about it. If we keep doing arc sines, eventually the mathematical world, they're going to change their mind, aren't they? And they're going to start calling it this again. Yeah, I feel so much better I got that grump out of me. I love America. I think it's the best country in the world, and next to Scotland. So I do love you, but you drive me crazy sometimes. Back to this question. Do you recognize it as a product rule? Right, so we're going to do inverse trig functions with a product rule. And so its derivative is going to be f dash g plus f of g dash. Don't expect much in the way of style points. These answers are typically just ugly and you can't do anything about it. If you differentiate an inverse cosine, you get -1, that guy, times g, plus leave this guy alone. And if you differentiate a natural log, don't you get 1 over x? And would you agree that, I guess I could do a minor tidy up, but it's so minor, I'm not even sure it's worth writing down. Isn't that as good as that answer's going to get? There's nothing you can do to make it pretty. And that is an example of a product rule. Let me show you a product rule that does have some style points in it. Square root of 1 minus x squared. Take away x, inverse cosine of x. And we are going to make that or differentiate that. Well, let's do some tidying up. Would you agree that you have to call this a half power if you're going to differentiate it? What method am I going to use to differentiate this piece? Because there's two separate parts. This part we're going to use chain rule eventually, but what's this going to be? How do you differentiate x cosine x? What method do you use?
A product rule?
Yeah, product rule. And that negative's a bit of a pain. If I include it with the f, that means I don't need to worry about subtracting something later on, right? And it just gets messy and I forget to do it anyway. So this guy, something to the half is 1/2 1 minus x squared times the derivative of 1 minus x squared, which is negative 2x. And this, oops, to the power of negative a half, almost forgot, right? Multiply by the power, reduce it by 1, times the derivative of that. These cancel out and get x. This guy goes downstairs. And then this becomes that. So if you want to differentiate the square root of 1 minus x squared, call it 1 minus x squared to the half and use the chain rule with a power rule. So multiply by the power, reduce the power by 1, times the derivative of the inside function, which is negative 2x. The negative 2 and a half cancels, so that's where the negative x comes from. The negative a half power comes downstairs as a positive and then becomes a square root. So far, so good?
Just a real quick question.
Yeah.
So do we only add like ln when a variable is in that power? Like if it was 1 minus something and then to the power of 1 over x, you'd then use the ln?
Yeah, you'd use the ln if it was 2 over x or 2 over something or whatever. The log function only gets used, that ln bit that you're talking about, only gets used when there's a base to the power of some function of x. So I'm trying to find my little list, which I cannot find now. So under here, there it is. Guess what? There it is. So that ln that you're talking about only happens when there's a number here. So 5 to the x or 5 to the sine x, you would get this guy, right? If it was x squared or x cubed, you would use the power rule, right? So, side issue. There's two guys. Look similar, but they're totally different derivatives. Top guy is power rule. Bottom guy has that log thing in it. Do you see the difference between when you use it and when you don't? Does that help? We good? Right. So back to this fella. Product rule. It's going to be f dash g plus f of g dashed. Since I am counting that negative as belonging to the x, I don't need to make a minus and subtract everything. That's why I'm doing it that way. So if you differentiate this guy, you get negative 1 times that guy, plus that guy times this fellow's derivative. And this fellow's derivative is 1 over the square root of 1 minus x squared. So what do I get? I get negative the inverse cosine of x. Inverse cosine also has a negative. So plus x over this guy. And didn't I promise you that this one would have some style points? Can you see anything that cancels here? What cancels?
Fractions have the same denominator.
And that's a plus and that's a minus. So essentially, don't they just cancel each other out? And so the answer is negative the inverse cosine of x. So the derivative of that ugly function here actually was quite nice. Okay, I got one last guy to do, and we have just enough time to do it. Well, since it's the last one of the set, you got to expect something extra special. I refuse to call it an arctan. It's an inverse tan of a square root. And I'll warn you right now, this is not your typical question. This is like the worst case scenario. So don't expect to get many, if any, to look like that. I wouldn't give you an exam question, for instance, of this degree of difficulty. There's just too much going on. But it is good to look at, ultra difficult questions. It helps you get an idea of what's going on. Now, It's the inverse tan of a really, really ugly function. Agreed? That is not a pretty function in any way, but we're still going to differentiate the inverse tan of it. Well, according to our rules, isn't the derivative of an inverse tan 1 over 1 plus the thing? Oops, one big square root, the thing squared, followed by the derivative of the inside function. Okay, I'm going to leave that guy for a while and focus on making this a little bit prettier. So it's 1 plus the square root of something squared, essentially cancel each other out. And I now have that. I'll put a little bracket around it. Would you agree that is downright ugly, but it's right now that's as good as it's going to get. So far, so good. Right, now, I have to find the derivative of this ugly fraction. And you can tackle it in all sorts of different ways. I could, but I'm not going to. I could just call it 1 plus x, 1 minus x to the half. And couldn't I do a chain rule? But wouldn't that be a really weird chain rule with a chain rule inside a chain rule? It'd be really messy. I don't want to do that. So I'm going to do some algebra on it, and I'm going to call it 1 plus x over the square root of 1 minus x. And then I'm going to call it 1 plus x to the half over 1 minus x to the half. So what I'm really doing is I'm making it essentially a quotient rule. Agreed? If you try to do it this way, wouldn't you have to do a chain rule with a quotient rule inside it? And oh God, I wouldn't even want to know where that would go, but it wouldn't end well. So call this f, call this g. To get the derivative of it, it's going to be f dash g, take away f of g dashed all over g squared. We've got 5 minutes to go, and we'll probably need every single one of those minutes. If you differentiate 1 plus x to the half, you will go a power rule. You'll multiply by the power, you will reduce it by 1, technically times 1, it doesn't matter. And then you'll leave the other one alone, which is 1 minus x to the half. Take away, leave the first one alone. And if you differentiate the bottom, you get 1 half, 1 minus x to negative a half, times the derivative of that, which is negative 1. And the whole thing is that guy squared. Well, that guy squared is just 1 minus x. So what do I have? I have 1 half, 1 plus x to the negative a half, 1 minus x to the positive a half, take away 1 half, or 2 takeaways, add a 1 plus x to the half and a 1 minus x to the negative a half all over 1 minus x. Right, is that not scarily ugly? Right, no way in the world that is not scarily ugly. Secondly, style points. I haven't even went near style points on this. But I'm going to take it as is. That's this thing here. I can pull out, the only thing I can pull out is a half. And now I'm left with a 1 plus x to the negative a half, a 1 take away x to the 1 half, this fella, and I have a 1 plus x to the half and a 1 minus x to negative a half. I'll pull out that a half. See this guy? He's going to go in the bottom. Like that. And the top is just going to be this ugly fractional power plus this equally ugly fractional power. Okay, so I got everybody together now we're going to see if we can make things work a little bit. There's that
I have
too.
a question.
Yes.
When you were differentiating it on the page on the left, is there a reason why the 1 minus x isn't squared?
With this thing here? Or down here?
Yes. Is the denominator not squared?
Yes, but the square root of 1 minus x squared is 1 minus x.
Oh, okay. Okay.
I just did it, you know.
I see.
Oh God, look at this guy. I'm actually going to multiply these out. If you do this guy times 1, you get 1 minus x. And if you do this guy times this fraction, you get 1 plus x. And can I just say dot, 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 meaning I haven't done anything at the top. But that cancels with that, and 1 plus 1 gets you 2. So now I've got 4 in the bottom. Well, that was something, right? Every little bit helps. Right, we're 2 lines away. We've got to be quick. This combination here can be written as 1 minus x to the positive a half and a 1 plus x downstairs. The second fraction can become 1 plus x to the half, and the negative power can be 1 minus x to the half. Since the whole thing's over 4, let's just call it a quarter. And to finish with, the square root of 1 minus x over the square root of 1 plus x, add the square root of 1 plus x over the square root of 1 minus x. Finished. That is an inverse trig function from Hades, isn't it? It is just, sometimes it's nice to just take something really horrible and try and find it. You might be able to play about with that, but I don't think anything you could do to this weird combination is probably going to bring anything to the party. It's just going to look different, but a different ugly, not a better looking one. Right, make sure you got your last name and call it good. I'll hang about for some questions. And we learned some clever stuff today, I think.
I had a question for like the naming of like the arc sign. Does it what about like arc length? Like
I don't think it comes from that, but I know what you're talking about. There's terms like arc length. I don't think it comes from there. I think it's just a coincidence of naming.
oh.
I'm guessing, don't quote me on this because I'm 9 times out of 10 and I guess I'm wrong. I think it might be something to do with Latin, where arc might mean something like the opposite of, and so arc sign might mean the opposite of a sign, you know. That would be a off the top of my head guess, but it's a total guess.
Okay.
And wouldn't it be just better if you don't use the darn thing, then I won't need to get annoyed?
Yeah.
Right? In fact, why don't we start a good habit? You know, we've got to start somewhere in America. Why don't all of you use inverse signs and never write down arc signs again?
It is easier to write the not arc. Yeah.
The inverse is easy.
Have a good day.
Okay, guys. As I say, I'll see you tomorrow. Any other questions?
I have a question
Mm-hmm.
from homework number 8.
And what section is it in? The same one we're doing right now?
Yeah, this chapter. Yes.
Oh, good. Okay, so let me find my version of 8.
Okay.
I have the natural law. No, I don't. That's 9. I think it's 4 to the z log to the base 4 of z. Do you have a different base?
Yeah, I have like 3, but it's same.
Okay, that's fine.
Yes.
Right. So what I'm seeing here is a product, Joe. This is f, and this is g. Okay.
Okay.
So when we differentiate it, it's going to be f dash g plus f of g dashed. If you differentiate 3 to the z, we're using this rule here. So the answer is natural log of 3 3 to the z. Untouched, untouched, this guy is, well, untouched yet, is log to the base 3 of z. Good. Now, leave this guy alone, you get 3 to the z. If you differentiate this fella, you get 1 over a z, and the natural log of 3 goes here. Are we good with that? F dashed g plus f of g dashed. We go with these 4 pieces.
Yeah, I got so far, but I
Okay.
don't know what to do the next.
Well, what I'm going to do here is 3 to the power of z is a common factor. And I'm going to say log to base 3 times log to base z plus 1 over log to base 3 z. And that's as good as the answer is going to get, I think. Is there anything I should be cancelling? Let's see. Oh,
So what did you do the log base 3?
yes. Right, so 3, right, when I differentiated, oh, shooting space. No, I'm right, I thought I made a mistake. What was your question?
What did you do the log 3? How did you multiply?
Where did it come from?
Yeah,
Is that-
yeah, yeah. On the top.
Okay.
Natural log 3 times 3d times log 3. How
Oh.
did you?
How did I get this piece?
Yeah, the next the log 3.
Okay, let's get that out of the way. If you differentiate 3 to the power of z, then you get log to base 3, 3 to the power of z. So that's it.
3. Oh, you did common factor.
So I differentiated, that's a bad place to put it. If you differentiate 3 to the power of z, you get 3 to the power of z with the natural log of 3 tagged onto the front.
Oh, yeah.
So that's where that piece came from.
Okay.
I'm looking at my answer and I'm looking at theirs, and they've done a different version, and I have an extra one of these and they lost it. So why did they lose it? How did they lose it? Because this here is log to the base 3 of z. Oh, okay. So if you take the natural log of, try to write this down. If you take the natural log of 3 times the log to base 3 of z, right? If you take that combination, according to them, that can become the natural log of z. So all of this is the same thing as the natural log of z. And I'm pretty sure what they did is a formula called the change in base. I wouldn't worry about that. I would just leave it like that. I don't think you need to know that this ugly combination actually ends up being something relatively nice.
Okay.
So hopefully it will take this version here, but if they don't, replace all of this, right, by just log z, and it will work.
Okay.